Welcome back. In this tutorial, we'll be going through several of the commands that are used for regression analysis. We will cover this for both the case of a continuous Y output, where we use terms like multiple linear regression, stepwise regression, and best subsets regression. And then at the end, I will go through some commands that we use for the binary logistic regression, the special case where we have a 0-1 output. There are several data sets for this. They are attached in an Excel file. You can just copy those Excel files into Minitab, copy the columns of data over, and we will start from there. In particular, here is a list of the various tools I'm going to show you. There's not screen snapshots of each of these, but I'm going to go through them each one by one, how I would use Minitab to do that. And you can take notes or play along as you go through that, and hopefully you'll pick up on the various commands needed. At this point, I'm going to switch over to Minitab. You'll notice that I've copied in some data sets. So if I were to go to the Excel file, there is a data set, for example, on tire pressure. And there is a section of data. There is one on pump vanes. And this is one which has a continuous Y output, as discussed in lecture. And there is one on a luxury home case study, which is a binary logistic regression analysis. Let's jump into our Minitab. We're using Minitab version 17 in this module. The first thing I want to demonstrate is the correlation tool. If we were to have a bunch of variables, for example, several of the variables for the pump vane data, several of the X's, if I wanted to look at how each of those were correlated with each other, as well as correlated with our Y output, one of the initial things I can do is I can go to Stat, Basic Statistics, and click on the Correlation button. And under the Correlation button, I can highlight several of the variables I'm interested in. Suppose I wanted to highlight all the way down through here. I can click those over. I must have clicked on a wrong one. So I have the PTFE. Oh, I can't do cavity. PTFE, V-length, squareness, radius. I'm just clicking on some different variables. You'll notice here it says display the p-values. And it also tells us to use the Pearson correlation coefficient. Now, when we hit OK, it makes a matrix for us. Across the top of these are all correlation coefficients. And then down below is the p-value. When the p-value is low, we believe that the correlation is not equal to 0. And therefore, we have some type of relationship between our variables. For example, v-length 3 and v-length 2 have a really strong correlation. To graphically show that, I can always come over and do a scatter plot. So graph, scatter plot. I can even put in a regression line if I'd like to. And I can put in two of my variables, v-length 2 and 3. Hit the OK button, and you can see this very strong relationship in this data set between the two length measurements at the two locations. Next up, I want to talk about regression analysis. When I do that, one of the things I can do in regression is I can start to look for relationships between X's and Y's. And one way to do that as a screening analysis is to do a fitted line plot. Let's just take this same data and click on fitted line plot. And our output variable for this particular study is the current draw. And suppose we look at the input variable v-length 3. If I hit the OK button, it comes back and it gives me a fitted line plot. Fitted line plot gives me an equation. It tells me the inherent S about the fitted line and the R squared and the R squared adjusted values. Typically, we're looking for higher R squared values. In this particular example, we have lots of variables at play, not just v-length. So not surprisingly, we don't have perfectly or R squared that's super high. In this case, there's other variables that are probably explaining some of the variation about that line. For another example of a fitted line plot, suppose we were to come over and use a different data set. This time I'm going to regression, fitted line plot, and for my y output, I'm going to use a variable which is a coefficient of rolling friction, and I'm going to look at that versus the tire pressure. So I have this study where I'm looking at different tire pressures in bicycles versus a coefficient of rolling friction. If I hit OK, I can come over here, I create a fitted line plot. You'll notice, though, that in this particular case, there appears to be some bend to my data set. And even though I have a rather high R squared, I think that there may be a better model fit out there. In this particular case, I can rerun the last tool, either using the Edit Last Dialog box or Control E. And this time when I use my fitted line plot, I'm going to switch that over to a quadratic fit. And when I do that, I now get a model with both a x term as well as an x squared term, and now I have a really fantastic fit to the model. Clearly there's a very strong predictability here between the pressure and the coefficient of rolling for this case. I'm just trying to show you in this case some different ways of looking at that. Sometimes a fitted line plot quadratic is a better representation of our data set. Next up, I want to start talking about multiple regression. I'm going to come back and use the pump vane data. Things of note, my y output is the current draw. So my y output in this example is the draw, the current measured in amperes. That's just a unit of measurement. And of most importance is to note is that that is a continuous variable. And then over here, I have a lot of additional continuous variables. These are all continuous x's. The cavity here is a different type of variable. It's categorical in nature, and we would model that one separately. Even though we use numbers here, this is really could be thought of as categories A, B, C, and D. To use regression, we go to Stat, Regression, Regression, Regression. So we have several layers down to get to fitting a regression model. And we can start out by looking at the response being the draw, and then it says continuous predictors. And we have different variables here. We have glass, PTFE, we have the V length, and I'm going to hit the shift button and go all the way down to thickness 3. Oops. Something happened there, so let me do that again. So stat, regression, fit a regression model. I have the response as the current draw. Continuous predictor there is glass. And I'm going to select my various x's that are possible. Move them over to the continuous. And this time I'm just going to regular run old regression. When I do that, I scroll up and it says, you just ran a regression analysis. Minitab comes back and does a p-value for all of the variables. In this particular case, you'll notice that V length is important, particularly V length 3. We'll notice that thickness 3 is important, and there are a couple of other ones that are on the fence, maybe squareness B and perhaps the V length 2. Now if I scroll down, I look at my model summary. Here is my S. You'll notice from before I did a fitted line plot that S was 0.3. When I use several variables, particularly significant ones, I now reduce that inherent S down to 0.15, and my R squared now goes up to 83.9. As we discussed in class, with multiple regression, R squared adjusted is a more generally accepted measure because it would penalize you for extra unnecessary variables. It gives you coefficients for everything, and it gives you a nice little regression equation. Now the challenge here, or the concern, is several of these coefficients are not significant. So I'm overfitting a model with terms that do not matter. At this point, I can either start to remove one at a time, or I might take a shortcut and remove anything above a 0.15, and then start to remove things in that 0.05 to 0.15 p-value range, and try to work my way down to a final model. Alternatively, I can go to Stat, Regression, Regression, and this time when I fit my model, I'm going to click on the Stepwise button. What Stepwise does, it defaults first of all to none. I'm going to come over here and change that to Stepwise. And it's going to do both a forward-backward mix. And what Stepwise is going to do, it's going to run through an algorithm and identify which variables are going to create a best model. Now, I got to be a little careful here because it may not be the true optimal, depending on which combination, the order in which I put variables in there. It could be not necessarily the final best version or the best, most optimal model, but it's going to be awfully close. In this case, I can establish some values to either put in or out of the value. These are p-values. Under hierarchy, I can even kind of control which terms I want to put in there. I'll leave it default. And down here, I actually like to include the details for each step. When I hit OK, I scroll up and Minitab comes back and says, you just did a stepwise regression. Step 1, it put in the thickness 3 along with a constant term. And when it did that, it got an S and it got an R squared. And the R squared here is around 73%. Then for step 2, it added the V length. And when it put in the V length, this was also significant, and R squared jumped up to 82, 83%. Now that I have two predictors, I can start to look at the R squared adjusted. And I noticed there that it's a reasonable shift, and I also get some reduction in the inherent S. So I'm explaining more of the variation in Y. Then I can look at a third variable. This one comes up as squareness B. Now squareness B is not at 0.05, but because I told it to use 0.15 as a criteria, it gave me the option for that model. In this particular case, I notice I get a rather small bump in the R squared and almost no change in the S. Therefore, I would probably come back with a final model with just the thickness and the V length. If I wanted to, I could come back and do Stat, Regression, Regression. And this time, for my predictors, I'm just going to put in V length 3 and thickness 3. Hit the OK button. And when I do that, it comes back and creates a model with just those terms. I did not turn the stepwise off. That's what I should have done as well. Here are the two terms. They're both significant. Here's the R squared value. I didn't need to do this because it's already done. And here is my regression equation. You'll notice it's just reading the coefficients from this table. Something else I may want to do is when I do this regression analysis, under graphs, I can also click on the 4 and 1. I could have done this first, but I'm going to do it here at the end. If I hit OK on the 4 and 1, when it runs the model, it produces the following plot. When I do that, I can notice that the normal probability plot, it reasonably fits this line. There's a little bit of points that are a little bit odd, but overall it's not too bad. I have somewhat of a normal shape histogram here, and if I look at the fits, this seems reasonable for constant variance. As we discussed in class, we're looking for really obvious differences. The more you do this kind of analysis, the more you see that when there really is a nonlinear relationship, it should be a lot more clear. Just as a little aside, let's say I went back and did my stat regression analysis, and I went back and I did the coefficient of friction versus the pressure. And under graphs, I told it to do a residual plot. When we did that, now we get some strange kind of looks to things that we want to be more careful of. That wasn't real critical, but just sometimes when you have nonlinear data, go and do the regular regression with the fitted line plot, and you'll see some of the oddness or the unusual things that happen in the graph. Let us move on. We've gone through the stepwise regression. As I mentioned in class, sometimes people criticize stepwise because it solves for a single answer. And people might say, well, give me choices of different models, especially ones that are very similar to each other, and let me decide what I think is the best model based on my understanding of the variables involved. For example, it may be easier to explain to somebody else certain variables versus other variables. If I wanted to do that, I can come back and do a best subsets. Now I will do stat, regression, but this time I'm going to click on the best subsets command. When I hit the best subsets command, now I have to put in some response and predictors again. I am going to come back and put in the draw as my response. And then for the predictors, I have glass, the PTFE, the V-length, squareness, radius. I'm putting them all back in. And when I do that, it comes back and says, here is your best subset result. And I know it's a little hard to read on the screen, almost impossible. But you'll notice here that for every increments of 2, they give me 2 choices. So with variables with only one x in it, here are 2 choices. Here are 2 choices for variables with 2 in it. When I did it with variables with 2 in it, I have a choice. Either I have v-length 3 and thickness 3, or I have v-length 2 and thickness 3. Given that v-length 2 and 3 are highly correlated, as we showed earlier, probably either one of them would have been fine. I get a slightly higher r squared. In reality here, this is an observational study, so when I change one dimension, I'm probably changing them both. And that's why they're coming up to be similar models. In this particular case, we got the same answer from different perspectives. In other cases, we might get a slightly different answer. Of note here, when I ran the best subsets under options, it says models of each size. In other words, if I have this number at 3, it'll make 3 of each. So for 2 variables, it'll make the best 3 models. For 3 variables, it'll make the best 3 models. I can even limit this, so I could say, well, I'm not putting more than 4 variables in a model. And when I do that, it restricted itself to only models with 4 or less, so 1 to 4 variables or 1 to 4 factors in the final model. You will notice that another way of looking at this is for almost all the models, thickness 3 comes out and v-length 3. So going across the 1, 2, 3, and at least especially the 2, 3, and 4, the same 2 tend to dominate. You will notice that the next variable coming in appears to be squareness b as the next variable that appears to have a slight impact. Of course, we ran the p-value for that, and the p-value was above 0.05. In fact, it was above 0.1. So even though it is the next one in, arguably it's not a significant variable having an impact on our ability to explain the variance in y with our regression model. The last example I want to walk through is if I want to put in a categorical variable. This time we're going to do stat, regression, regression. Let's just fit a regression model. I'm going to turn the stepwise off. My regression model, current draw, my variables, I have v-length 3 and thickness 3, I think, were the ones I could pick. And then I'm going to add another variable. I'm going to add the cavity. This is a categorical variable. It's listed as 1 through 4, but they could have been A, B, C, and D. These are just 4 different categories. When I do that, I hit the OK button. There is my residual plots. I don't see anything of major concern. I scroll up here, and here is my regression analysis. It comes back and gives me p-values for 3 of them. In this particular case, the cavity has 3 degrees of freedom because there were 4 cavities, and it has a p-value of 0.867, suggesting that there is no difference by cavity. However, because I told it to do it for the different cavities, it went ahead and created 4 different regression equations, 1 for each category. In this particular case, we wouldn't use 4 different ones. I would remove the cavity term and go back to my original model. Now, if cavity was significant, or if one of the levels of category was significant, I might pull the model out and say, okay, for cavity 3, here is the model, and for cavities 1, 2, and 4, here is my prediction model. Now, in the world of manufacturing, when I have different cavities of a mold or different machines making the same part, I do not want to have different regression equations for each. I want to be able to make all of those different machines or molds or dyes all behave the same so that I can remove that as a noise factor. One more thing I'll show you. In their stat regression, there are also some options for some different plots. A nice one is a response optimizer. It actually can be used to solve for x, or solve for y, or find the best x's to get the y I would like. And there are also factorial plots. And there is a prediction tool. So if I wanted to put in some values of x, I can predict my y. Now, when you use these tools, I'm going to recommend that you wait till after you have a final model to use them effectively. As example, if I have a factorial plots, I could put in my variables, v-length, thickness, and the cavity. For the 2 v-length and thickness, it makes lines because there are several values in the data set for those. For the cavity, here's my 4 different cavities. You'll notice here that the averages are all pretty similar to each other. For the prediction tool, I have stat, regression, regression, prediction tool. I have different variables. Let me do this first. Let me do stat, regression. Let me remove the cavity term because it's not significant. I reran it again. I have my model with v-length and thickness. If, for example, I wanted to do a prediction, I could come over here to regression, regression, and predict. And for my value of v-length, I'll have to put in some values. I should have looked ahead of time for the v-length values. Let's say I put in a value of 23 and a thickness of 3. I'm just making up numbers. I have no idea if they're going to work. And when I hit OK, it comes back and it solves the equation and it comes up with a fitted value. I don't think those are legitimate numbers, but just showing you the process, it would actually solve the equation given some values of x. The last thing I want to do is I want to come in here and show you binary logistic regression. For this one, I'm going to use the luxury home case study. Here are my variables, square footage, some different features which are all categorical. To illustrate some of the binary logistic regression tools, I can go to Stat, Regression, Binary Logistic Regression, and I'm going to do a binary fitted line plot first. So let's do a binary fitted line plot. My response is by elsewhere. The event is 1, and the predictor variable here, let's do that for the square footage per room. We will go ahead and hit OK, and it makes this curve as I showed in class, as well as gave us an equation. So if I told you the square footage per room, it'll make a prediction in terms of the probability of the event. You'll notice here under the options there are different functions. In this particular case we use the logit function. There are other kind of functions we could do. Also you'll notice here that odds ratio are based on increments of 1. If I want to do this for every 25 square feet, I can change that value. Under the graphs, I can also do a residual plot. And I can uncheck the display the observed proportions. But I can check the confidence intervals. I'm going to hit OK, and here I have a nice prediction curve for square footage per room and its impact on the probability of an event. Now I'm going to be very careful here. I have other variables that could be significant here. This is just looking at it as an individual, so this could be adjusted based on the impact of other variables. For some screening, I can do binary fitted line plots on the different continuous variables. I can also do factorial plots. Stat, regression, binary logistic regression, and I'm going to do some plots. But before I do that, I have to fit a model. And to fit my model, I come over here, and under the response, I plug in the by elsewhere. Then again, I have the event is 1, and I have some predictors. One of my predictors is the square footage per room. Now I have a series of categorical predictors. Front dining room, side addition, non-local, high family room, and semi-private. Because I have several variables, I'm going to go ahead and use the stepwise version of this. This is going to run through an algorithm to try to pull out the ones that have the most likely to be in my final model. And when I do that, I come back and I get a result. Here's the binary logistic regression. There's 180 samples in this data set. Minitab tells me I have 120 events. These are all the ones coded 1. It gives me a p-value for my variables. In this case, I have 4 variables that came up significant. My r-squared numbers here are based on around 30-some%, which is not great, but not surprising for this type of analysis. It also gives me an odds ratio for the different variables. These odds ratios are based on the coefficients that were provided. As I mentioned in class, sometimes the odds ratios get a little confusing. And also I have lots of equations because I have lots of combinations of my variables. To help me visualize, rather than use the odds ratio, I'm going to go to Stat, Regression, Binary, but I'm going to use factorial plots. And this time for my factorial plots, I'm just going to go ahead and put in all the data. I'm going to hit the OK button. And when I do that, it came back and gave me my significant variables. In this case, I have the front dining room, non-local, semi-private. Front dining room, non-local, semi-private. And I have the square footage per room. For this particular graph, I might want to come over here and go to and add in a y-axis label or a scale. Oops, sorry, I should do that again. So I can go to Stat under the select item, add, sorry. Under the add command, it said add a reference line. I put in a reference line at 667. That's the overall data set. And this helps me visualize the impact of each of my variables. In this particular case, I have higher square footage. I know that front dining room 1 is good, front or non-local 0, and semi-private 0 all give me a higher probability. If I wanted to make a prediction, I could come over here to Stat, Binary Logistic, make a prediction. In this case, my square footage per room, say I want to put it at 280. Where it says front dining room, I want that to be a 1. Non-local 0, semi-private also a 0. If I put those in, by the way, there's my model, has those variables in it. I put those in, I hit the OK button, and it comes back and it says the probability of that person buying elsewhere with a large home, wanting a front dining room, with the other settings of zeros for non-local and semi-private, the probability of them would be 0.98 to buy elsewhere, or 0.988. In other words, you can generate prediction models given a set of x's once you have a final model. You'll notice here that this regression equation, this is the regression equation shown. This y prime is the model. So if I told you what the values for each of those were, that solves it for the y prime. Sometimes I just want to look at two variables at a time where they're both categorical, or categorical in the binary. If I wanted to do that, I could come over to Stat, Tables, Cross Tabulation in chi-square, and I could put in the buy elsewhere, and then put in one of my variables, for example, the front dining room, put in the counts and the column percents, and it would make this little table for me. This is the table that I showed in class, which lets me know that the front dining room equal to 1, the percentage of people that bought elsewhere went from 67 to 80.4%. Also, with a cross tabulation in chi-square, I can click on the chi-square test, hit OK, and it'll generate a p-value for me. I did the binary logistic regression approach. This would just have been another way of looking at that. There are times that it's helpful. The factorial plots may be easier for you to understand, but just giving you some different options to look at. The last thing I want to do is talk about event probability plots. This time we're going to do this. We're going to go to Stat, Regression, Binary Logistic Regression. I'm going to fit a model, but I'm going to fit a model with the square foot per room and the front dining room, just as two variables. When I do this, I'm going to go to the storage command. And I'm going to store the event probabilities. These are the fitted values for all combinations of those. Then I'm going to hit OK and hit OK. And when I do that, if I go to my data sheet, you'll notice there's a new column here that says fits. These are the fitted probabilities given my values for the settings. I could do the exact same thing if I use the prediction tool. But now I'm actually want to generate a column for all combinations. Now, to visually show somebody with a loss function, I can go to Graph, Scatter Plot. I'm going to use Scatter Plot with Connect and Groups. I'm just recreating what I did in lecture. I put in the fits for the Y, and my X variable is the square footage per room, and my other variable is the front dining room. And when I hit OK, it gives me a couple of curves, one for each of the combinations of front dining room and the two combinations of the front dining room. Let me repeat this. Suppose I wanted to put in two variables or two categoricals. I could do stat, regression, binary logistic. Instead of just having front dining room, I'm also going to put in the semi-private factor. I've hit OK. I've run a model. When I did that, it now stored another column of fits. This time when I go to Scatter Plot, I'm going to put in a graph with fits 1. Let me do this. Let me clear these out. Fits 1, and then for my X, I've got square footage per room, and then I have front dining room variable as well as the semi-private. I hit OK. And now I have a line for each of my combinations. What's going to start to happen is I'm going to start to run out of data for everything. I won't observe everything along the way. In all these cases, though, I can see this general relationship on square footage per room. But I can see the impact is changing a little bit based on the combinations of front dining room and semi-private. In other words, for each one of these, I can make a prediction of what is likely to happen. Now, these are all predictions, of course. We'd have to go out and do some confirmation studies if it was feasible, or maybe study some of these under more controlled conditions. Because these were just observational studies, we were changing a lot of variables at the same time. Maybe we should go back and do more of a controlled experiment to be able to look at these things in a more controlled way. I know I went through a lot of things here, but if we go back to the list here and we go back to the lecture notes, all I did was walk through all the different things that I did in lecture. A lot of these things you have to do a few times, a few problems and examples, and hopefully they'll become fairly straightforward to you. There's definitely a pattern to these various tools with regression. That's all I have, and good luck.